Hello everyone, this is Abhishek Mahanti and welcome to lecture number 15 of the chapter Electric Charge and Field. In the previous lecture, we had discussed about area vector and electric flux. Today, in this lecture, we will discuss about a very important theorem or a very important law of this chapter, and the name of the law or the theorem is Gauss Theorem. So, let's get started. So students, in the previous class, we had derived a formula to calculate electric flux linked with a surface. For example, suppose we'll choose a small element, and suppose ds is the area of this element. Then the area vector will be directed perpendicular to the surface. This is ds vector. And suppose the electric field lines, they are directed along this direction, such that the electric field makes an angle theta. The electric field makes an angle theta with the area vector. Then, to calculate the small amount of electric flux linked with this element, we use the formula d phi e. d phi e means the small amount of electric flux linked with this small element. So d phi e is equal to the dot product of electric field and the area vector E dot ds. d phi e is equal to E dot ds. Since electric flux is the dot product or the scalar product of two vector quantities, it is a scalar quantity. Electric flux is a scalar quantity. So this Gauss theorem establishes a relationship between two quantities. The first one is the total amount of electric flux linked with a closed surface, and the total amount of charge or the net charge enclosed within the closed surface. So remember that Gauss theorem establishes a relationship between electric flux linked with a closed surface, electric field linked with a closed surface. Remember this term, closed surface. So it establishes a relationship between electric flux linked with a closed surface and the net charge enclosed within the surface. Net charge enclosed within the surface. So Gauss theorem establishes relationship between these two quantities, the electric flux linked with a closed surface and the net charge enclosed within the surface. So now I will write the statement of Gauss law and then I will explain it. So what is the statement of Gauss law? Gauss law states that the surface integral of electric field over a closed surface is 1 by epsilon naught times the total charge or the net charge enclosed within the surface, or within the closed surface. Don't forget to write closed surface, because this closed surface is the key in the Gauss law. Again I am repeating the statement. It states that the surface integral of electric field over a closed surface is 1 by epsilon naught times the total charge enclosed within the closed surface. So remember that I have mentioned this closed surface while talking about Gauss theorem or Gauss law. So this closed surface is very important. When we are using the Gauss law, we have to consider a closed surface. Is that clear? So now let us try to understand what is the meaning of this statement. It states that the surface integral of electric field. It means we have to integrate the electric field over the surface of a closed body. The surface integral of electric field over a closed surface. So how can we write the statement in mathematical form? So surface integral of electric field means E vector dot ds vector integration, and you have to give a symbol like this. This symbol represents the closed surface integration. So remember that Gauss law is applicable in case of a closed surface. If there is no closed surface, then Gauss law is not applicable. So this symbol represents the closed surface integration, and we are multiplying electric field vector with the area vector using the dot product. So E dot ds over a closed surface is equal to 1 by epsilon naught times 1 by epsilon naught times the total charge enclosed within the closed surface. So 1 by epsilon naught times into q, where q is the total charge or the net charge enclosed by the closed surface. So look at this formula. E dot ds means what? E dot ds means the small amount of electric flux linked with a small surface area element. So if we integrate that quantity over the closed surface, then what will you get? We will get the total electric flux to the surface. For example, suppose we have a closed surface like this, and if I choose a small area element here, if d phi e is the electric flux linked with this small area element, then d phi e will be equal to E vector dot ds vector. But if I integrate this quantity over the closed surface, I will get integration of d phi e. Integration of E dot ds means integration of d phi e, and integration of d phi e means the total amount of electric flux linked with the closed surface. So E dot ds closed surface integration is nothing but the total amount of electric flux linked with the closed surface. So this is the mathematical statement of Gauss law. Is that clear? Again I am repeating this statement. The surface integral of electric field over a closed surface is 1 by epsilon naught times the total charge enclosed within the closed surface. And remember that I am always emphasizing on the word closed surface. And remember that when you are using the Gauss law, you have to consider a closed surface. Without closed surface, you cannot apply Gauss law. So Gauss law has many types of application. It is easier to calculate electric field due to a continuous charge system or due to any kind of charge distribution by using Gauss law. So we will discuss about few applications of Gauss law, but now I will try to prove Gauss law. So remember that when you are using the Gauss law, you have to consider the closed surface, and this closed surface, the closed surface which is used in Gauss law is known as Gaussian surface. The closed surface which is used to use Gauss law is known as Gaussian surface. And the next question is how to choose Gaussian surface. What will be the shape of Gaussian surface? Remember that Gaussian surface can be of any shape and any size. We can choose a Gaussian surface of any size and any shape, but there is a problem if we choose any random shape of Gaussian surface. So remember that we have to integrate electric field, we have to integrate the dot product of electric field and area vector over the closed surface. And E dot ds means E ds cos theta. E dot ds means E ds cos theta. So when we are multiplying electric field with the area vector using the dot product, we must know what is the angle between E vector and ds vector. So if we choose a random shape of Gaussian surface, then it will be difficult to determine what is the angle between electric field and area vector. That's why when we choose the Gaussian surface, we have to be very smart, and we have to choose the Gaussian surface in such a way that the angle theta between electric field and the area vector is known to us. In most of the cases, either the angle between E vector and ds vector will be 0 degree or 90 degree. So we'll discuss about some applications of Gauss law, and in all those applications you'll see that either the angle between E and ds is 0 degree or 90 degree. So remember that always choose the Gaussian surface in such a way that the angle between E and ds is very easy to find, and then you can very easily calculate the surface integral of electric field over the closed surface. So never choose a Gaussian surface randomly. Be very smart while choosing the Gaussian surface. Now I will prove this Gauss law taking the help of a point charge. Imagine that we have or consider a point charge Q which is placed at a point O. This is point O, and at this point a point charge Q is located. And we have already discussed that the electric field lines due to this point charge, suppose this is a positive point charge, we know that the electric field lines due to a positive point charge is directed radially outward. So the electric field lines will be directed radially outward like this. These are the electric field lines. Is that clear? And with distance the electric field strength decreases, because we know that the electric field due to a point charge is given by E equal to 1 by 4 pi epsilon naught Q by r square. So these are the electric field lines. Now we have to use the Gauss law, means we have to prove the Gauss law. And what is Gauss law? Let me write the mathematical statement of Gauss law. E dot ds closed surface integration is equal to Q by epsilon naught. This is the mathematical statement of Gauss law, and we have to prove it. So look at the left hand side of Gauss law. So we have E dot ds closed surface integration. So I have told you that to use Gauss law you need a closed surface known as the Gaussian surface, and we have to choose the Gaussian surface very smartly, such a that the angle between E and ds will be either 0 degree or 90 degree. So for this point charge, I will choose the Gaussian surface in the form of a sphere, and the center of the sphere will lie at point O, and suppose r is the radius of the Gaussian sphere. So let me draw an imaginary sphere like this. This is the imaginary sphere, and this imaginary sphere has center at O, and the radius of the sphere is r. Remember that this Gaussian surface is a hypothetical surface, imaginary surface, and it is used to calculate E dot ds, closed surface integration E dot ds. So I have chosen a Gaussian surface in the form of a sphere. Now I will show you that if I choose a spherical Gaussian surface in case of a point charge, then it is very easy to calculate the closed surface integration of E dot ds. Let us see how. You can see that the electric field lines are radially outward, and since the surface, this Gaussian sphere, has center at O, all the points on this sphere are equidistant from the charge q. The charge q is located at the center O, and the radius of the sphere is r, and the center of the sphere is also lies at O. It means if you choose any point on the Gaussian surface or on the Gaussian sphere, all the points will lie at the same distance from the charge q. It means the magnitude of electric field at this point, at this point, at this point, at this point, at every point on the surface of the Gaussian sphere is constant, because we know that E equal to k q by r square. For a point charge, the electric field intensity has magnitude k q by r square. Since all the points on the surface have the same distance, are equidistant from the charge q, so the electric field strength will have the same magnitude at every point on the surface. And what are the direction of electric field? You can see that electric field lines are radially outward, and also the electric field lines are along the radius of the sphere. So if I choose a small surface element, at this point, then what will be the direction of ds vector? The direction will be again radially outward drawn normal. So here electric field and ds vector are along the same direction. Similarly, choose a small element here, ds vector. Again, the area vector of this element will be in this direction. So ds vector and E vector are along the same direction. So if you choose a small element at any point on the Gaussian sphere, you will see that E vector and ds vector are parallel to each other, and that's why the angle between them is 0 degree at every point. So you have seen that by choosing the Gaussian surface in the form of a sphere, we have made the calculation part very easy, because the angle theta is 0 degree at every point. But imagine that if you will choose the Gaussian surface in the form of a cube, if you choose the Gaussian surface in the form of a cube, then it will be very difficult to find the angle between E vector and ds vector, because electric field lines will be like this. So you can see that the angle theta between electric field and ds vector will keep on changing. If you choose a small element here, the area vector is along this direction. At this point, area vector is along this direction. This angle is 0 degree, but this angle is not 0 degree. Again, if you choose element here, the vector is along this direction. So if we choose a random, if we choose the Gaussian surface randomly, then the calculation part will be very difficult. That's why we have to be very smart while choosing the Gaussian surface. So now let us find the left side of the Gauss law, that is E dot ds closed surface integration, that is equal to E ds cos 0 closed surface integration, because E vector and ds vector are parallel to each other, so the angle is 0 degree. So E ds cos 0. So cos 0 is 1, and remember that the strength of electric field, E is the magnitude of the electric field or the strength of electric field at every point on the surface of the Gaussian sphere is same, that is k q by r square, or 1 by 4 pi epsilon naught q by r square. So since E is constant, I can take this E outside the integration symbol. So let us take E outside. We have integration of ds. So ds means what? Ds means a small area element on the surface. and if we integrate ds, we will get the total surface area of the sphere, the total surface area of a sphere. So here we have taken r as the radius of the sphere. So if the radius of a sphere is r, then the surface area, the total surface area will be 4 pi r square. So we will get E into 4 pi r square. Is that clear? E into 4 pi r square. So this is the surface integral of electric field. Now tell me, what is E? E is 1 by 4 pi epsilon naught q by r square. I have taken a point charge. So at a distance r from the point charge, the electric field has magnitude this much, 1 by 4 pi epsilon naught into q by r square. Now multiply 4 r square here. So you will get 4 pi r square will cancel. You will get q by epsilon naught. And this q is enclosed by the Gaussian surface. You can see that the charge q is within the Gaussian surface. So in this way we have proved the Gauss law. Integration of E dot ds over a closed surface is equal to q by epsilon naught. So this is the way you can prove the Gauss theorem or Gauss law. Now I will discuss about some important points about the Gauss law. The first point is that Gauss law is applicable. It is applicable for a closed surface. It is applicable for a closed surface. And if you look at this equation E dot ds, then E dot ds equal to q by epsilon naught, then this q refers to the total amount of charge present within the Gaussian surface or within the closed surface. Suppose we have a closed surface like this. Suppose we have a charge q1 here, minus q2 here, q3, minus q4, q5. We have 5 point charges. q1, q3 and q5 are positive charges, q2 and q4 are negative charges. And outside the surface we have a charge q6, q7, minus q8, like this. So inside the surface we have 5 point charges, outside the surface we have 3 point charges. So this q refers to, in the Gauss theorem, this q refers to what? The total charge inside the surface, total charge enclosed by the closed surface, not the outside charge. We have to ignore the outside charge. Means if we want to calculate the net charge enclosed by the surface, it will be q1 minus q2 plus q3 minus q4 plus q5. That is the net charge. Don't consider these point charges which lie outside the closed surface. So here q refers to the total charge inside the surface, total charge inside the surface. But look at the left side of the equation. We have E dot ds integration. This E refers to electric field. This electric field is due to the contribution of each charge, inside charge as well as outside charge. Because if a charge is at the outside of the surface, then the electric field due to that charge also results in some electric flux with the surface. So remember that when you are writing the value of q, only consider the inside charge. But when you are considering the electric field is due to all the charges, inside as well as outside. Because if a charge is placed outside the Gaussian surface, still the electric field produced by the charge particle will cause or will link some electric flux with the surface. That's why the electric field E vector is due to all charges. All charges means both outside charge and inside charge, both outside charge and inside charge. And you have to remember that when you are using the Gauss law, you have to choose a closed surface very smartly such that the angle between E and ds is either 0 degree or 90 degree. So this is some of the important points about Gauss law. Hopefully you have understood what is Gauss law, what is the mathematical meaning of Gauss law, and I have proved the Gauss law in case of a point charge. And this Gauss law, this Gauss theorem is a very important topic because most of the time you get long questions, the derivations in your exam. So this Gauss law has many applications, but in your syllabus you have total 3 applications. Means by using Gauss law we have to find the electric field due to a very long uniformly charged thin wire, and then we have to find electric field due to a very large or infinite plane non-conducting charge sheet, and finally we have to find the expression for electric field due to a charged spherical shell. So we'll discuss about all those applications one by one, but in the next class. So in the next class we will do the first application, then second application, and in the final lecture we'll discuss about the third application. So hopefully you have enjoyed today's lecture. We'll meet again in the next class. Till then, bye bye and have a nice day.